Why is chemical potential key to chemical reactions? Imagine a busy marketplace where goods move from one stall to another. Now, think of molecules and atoms as those goods, constantly shifting and reacting. Chemical potential is like the energy that drives these movements. It tells us how eager particles are to change places or combine. This concept is at the heart of understanding why reactions happen or stay still. Chemical potential measures how the Gibbs free energy of a system changes when 1 mole of a substance is added or removed. Gibbs free energy combines heat content and disorder, helping us see if a process will happen naturally. When particles react, their chemical potentials change, and the system tends to move toward a state with the lowest possible Gibbs free energy. This is what makes reactions spontaneous. Think of chemical potential as a push that encourages particles to react or spread out. If the chemical potential of reactants is higher than that of products, the reaction will tend to go forward to lower the overall energy. When the chemical potentials of reactants and products balance out, the system reaches equilibrium. At this point, no net change occurs because the energy, push, is equal in both directions. This balance is key to understanding irreversibility and equilibrium. If a reaction is spontaneous, it means the chemical potential difference caused an energy releases, making the process irreversible under normal conditions. When the system reaches equilibrium, the chemical potentials are equal, and the reaction stops changing. Chemical potential also explains why substances dissolve, evaporate, or change phase. For example, when a substance dissolves in water, its chemical potential in the solid phase is higher than in the solution, so it moves into the liquid. The same idea applies to boiling or melting, where the chemical potential across phases must match for equilibrium to occur. In practical terms, knowing the chemical potential helps chemists predict which way a reaction will go. It also allows them to calculate equilibrium constants, which tell us how much of each substance will be present at equilibrium. Changes in temperature, pressure, or concentration affect the chemical potentials, shifting the reaction toward or away from equilibrium. So, chemical potential is a vital piece of the puzzle. It links the microscopic behavior of particles with the larger thermodynamic picture. It explains why reactions happen, how they reach balance, and how energy flows within a system. Without understanding chemical potential, predicting and controlling chemical reactions would be much more difficult.